Hey calculus class, tonight you're going to learn topic 38, integration by parts, and this is a BC concept. So with integration by parts, we want to figure out how to undo the product rule. So typically when we have the product rule, right, when we take the derivative of two functions that are multiplying together, we take the derivative of the second times the first function plus the second function times the derivative of the first. In other words, if we have the integral of the first function times the derivative of the second function plus the second function times the derivative of the first function, that would equal a product of two functions. So if I wanted to split this up, I can split this integral up into two different integrals using our integral properties. Then what I'm going to do next is I'm going to move one of these integrals to the other side, and in this case I'm going to move the second one over. Now if I let u equal f of x and v equal g of x, then du would equal the derivative of f dx, and dv would equal the derivative of g dx. So now we can rewrite this as the integral of u dv equal to u times v minus the integral of v du. And that gives us what we call integration by parts. So for indefinite integration by parts, that means that if we have the integral of f of x times g prime of x dx, that will equal f of x times g of x minus the integral of g of x times the derivative of f of x dx. Or, in easier language, the integral of u dv equals u times v minus the integral of v times du. Now with definite integration by parts, it's pretty much the same idea. It's just from a to b. So after you integrate using integration by parts, that u times v has to be evaluated from a to b. Then you're going to find the integral of v du and evaluate that in terms of a to b. A couple things to keep in mind for integration by parts. The first, integration by parts is sometimes referred to as double substitution. The second, integration by parts is undoing the product rule, while u substitution, which is what we did yesterday, is undoing the chain rule. You want to try letting dv be the most complicated part of the integrand that fits a basic integration formula. You want to try letting u be the part whose derivative is simpler than itself. And then finally, sometimes integration by parts is needed more than one time. All right, so let's go ahead and do an example of integration by parts. So our first thing is to figure out what part is the u and what part is the dv. Keep in mind the dv will contain the dx. Okay. Now for the u, you want to pick the function whose derivative would be simpler than itself. So in this case, the function whose derivative is simpler than itself would actually be the natural log of x. And so I'm going to let u equal the natural log of x. So that means the dv is equal to x to the fifth times dx. And the reason why I did not let dv be the natural log of x is because I'm going to have to take the derivative of u, but I'm going to have to differentiate dv. And we don't know what the antiderivative of the natural log is yet. So I'm going to take the derivative of u, so I'm going to find the du, which would be 1 over x dx. I'm going to integrate the dv, so add 1 to the exponent, divide by 6. You're not going to worry about the plus c here. The plus c will come when you do the big problem. So now using the integration by parts says that you are going to multiply u times v minus, then you're going to integrate v times du. Okay? So the way that I always remember it is multiply the two that are across from each other and then integrate the two bottom ones. So when I set this up, I have ln x times x to the 6th over 6 minus the integral of x to the 6th over 6 times 1 over x dx. So I'm now going to have to see if I can simplify this integral and see if this is something that I can take the antiderivative of. And so the x on the bottom and one of the x's on top simplify. And x to the 5th over 6, that's just a power function with a multiple constant of 1 over 6. So yes, this is something that I can integrate fairly easy. So when I integrate, I add 1 to the exponent, which gives me 6, divide by the new exponent, which is 6. So that 6 joins this bottom 6, which gives me the 36. Then you add your plus c. All right. Why don't you see if you can try number 2 on your own? All right, let's see how you did. You should have let u equal x, because the derivative of x is pretty dang simple. So that means dv is sine x dx. I'm going to take the derivative of u, so du equals dx. I'm going to integrate dv, so the antiderivative of sine is negative cosine. Now when I set this up, I'm going to multiply u times v, subtract the integral of v du. So when I set this up, I get x times that negative cosine x minus negative cosine x, and that negative joined the minus sign, so that's why that turned to plus dx. And notice that I can take the antiderivative of cosine x, which is sine x, and then of course your plus c. All right, ready to learn the antiderivative of the natural log of x? All right, for this one, you're gonna let your u be the natural log of x, because you can take the derivative of the natural log of x. So that means that the only thing that's left, which is dx, that's your dv. Differentiate u, which gives me 1 over x dx, and I'm going to integrate dx, which is just x. Now I'm going to go ahead and multiply the u and the v and subtract the integral of v du. So when I set this up, I now have x times the natural log of x minus the integral of 1 over x times x dx. Notice these x's cancel, so that means I'm just integrating 1, which is just x. So the antiderivative of the natural log of x is x times the natural log of x minus x plus c. All right, now let's try one where we have to use the definite integral. So we have two functions, t and e of t. So let's say you let u be e of t, because isn't that a pretty simple derivative? The derivative of e to t is e to the t. So that means my dv is t dt. So now when I differentiate, I'm going to get that du equals e to the t dt. And when I integrate, I'm going to get t squared over 2. So now when I set up my integration by parts, I'm going to multiply the u and the v and minus the integral of v du. So my setup's going to look like the following. Notice how this piece, when I multiply u and v, since that's no longer an integral, I'm going to have to evaluate that piece from 1 to 2. Now, I want to integrate this piece. that looks pretty dang complicated. That looks more complicated than what I started with. So, since it created a more complicated integrand than what we started with, that means we should have chosen the u to be t. So, that's a good way to know if you chose the wrong u, okay? If you get to this setup and you realize that your integral that you now have to differentiate is worse than the one you started with. So now we got to back up and let's start over. So now let's use t as u. So that means dv equals e to the t dt. Differentiate, so du equals dt. Integrate e to the t, which is just e to the t. Multiply u and t minus the integral of v du. So now I get something that looks much nicer. Okay. Now I can integrate this integral. I can integrate e to the t. So, which is just e to the t. And for each piece, I'm going to evaluate from 1 to 2. And if you wanted to, you could rewrite this as the following. So I'm going to go ahead and plug in 2 for t and 1 for t and subtract them. And then this right here, the e minus e, that cancels because that's just 0. And then 2e squared minus e squared, well, that just gives me 1e squared. All right, let's try number 5. So for this one, I'm going to let u equal x squared. And dv is going to be cosine x dx. So when I differentiate, du is 2x dx. When I integrate, I get sine of x. Now when I multiply and then subtract the integral, I get the following setup. Notice, when I come to integrate this, I have yet again 2 functions multiplying each other, where one of the derivatives is not an inner function. So what this means is that we will have to do integration by parts again, but we're doing it on this integral. So that means I have to figure out what my new u is going to be. In this case, x, because it's going to be the simplest derivative. The dv's sine x dx. I'm going to differentiate, integrate. Now I'm going to set up the other integration by parts. So multiply and subtract the integral. Now when I set this up, this x squared sine x is going to come on down. This minus 2 is going to multiply everything that I set up for this new integration by parts. So now it's going to look like the following. Notice how I just brought down that x squared sine x, and this minus 2 is going to multiply everything by this integration of parts. So there's my u times v minus, since that cosine is a negative, that's why it turned into plus, the integral of cosine x dx. Now, this integral looks much nicer to what we can go ahead and integrate. So now, everything comes on down, and the antiderivative of cosine is sine. Since I did the antiderivative here, that means I have a plus c. Now I can go ahead and simplify this a little bit. I can distribute this negative 2 through. And notice how I have this negative 2 times c. It's just going to be some other constant. So off to the side, I'm just going to let c sub 1 equals negative 2c. So that my final answer is x squared sine x plus 2x cosine x minus 2 sine x plus c sub 1. And I think your book might use d, it says c sub 1, or it might use k. I can't remember, but I think it might use a different letter. All right, let's try this one. I want to see if you can do this one on your own. All right, let's see how we did. The u is x squared. Your dv is e to the negative 2x dx. when I differentiate x squared, I'm going to get 2x dx. Now, when I integrate e to the negative 2x, I have an inner function. So that means I'm going to probably have to use u substitution. So off to the side, and I'm using a different letter than u because I already have u floating around. So I chose w. So my inner function is negative 2x. The derivative of that is negative 2 dx. And I have the dx, but I don't have the negative 2. So that means I'm going to multiply both sides by negative 1/2. So now, when I resubstitute this in terms of w, I now have negative 1/2 e to the w du. Now this is something that I can integrate, which gives me the following. And then, of course, resubstitute in the w, which is negative 2x. So the v that I'm going to use is negative 1/2 e to the negative 2x. So now I can go ahead and set up my integration by parts. So multiply the u and v, subtract the integral of v du. So now I get the following. All right, now when I come back here, and I believe everyone should notice that this negative canceled out this minus, so that's why there's a plus. When I come to integrate this, you're going to have to notice that you're going to want to do integration by parts again. So u equals x. My dv is e to the negative 2x dx. When I differentiate, I get dx. When I integrate, you should notice that this is the exact same integral up here. So instead of doing all of this again, I already know that the antiderivative of e to the negative 2x is negative 1/2 e to the negative 2x. So now I'm going to go ahead, multiply, subtract the integral to get the following setup. And this term just came on down. Now I'm going to go ahead and integrate this, which is much nicer. And if you notice, we've already integrated that twice. So after integrating, I get the following. I went ahead and combined like terms. That 1/2 and this negative 1/2 gives me that negative 1/4. Of course, the plus c. I made a common denominator here, and I pulled out these two negatives and put it out in front of the fraction. All right, let's try this one. X times sine 6 of x. Your u should be x. Your dv is sine 6x dx. So that means my du is dx. And I'm going to have to use the u substitution here when I integrate. So my w is 6x. dw is 6 dx. I don't have a 6 here, so I'm going to have to multiply both sides by 1/6. So what I'm really integrating is 1/6 sine w dw. And the antiderivative of sine is negative cosine. Of course, the 1/6 comes along. Replace w with the 6x. So here's the v that I'm going to use. All right, now I'm going to go ahead, multiply the u and v minus the integral of v du. And of course, this negative cancels the subtraction sign. And when I integrate this cosine 6x, I'm going to have to do u substitution again. So that means my inner function 6x, my derivative is 6 dx, multiply both sides by 1/6. So now I am integrating the following. And this 1/6 just multiplied this 1/6. That's where the 1/36 comes from. Antiderivative of cosine is sine. And then, of course, replace w with 6x. So there is your final answer. All right, last one. Let's see how we do on this one. All right, you want to choose u to be e to the x. dv is going to be sine x dx. The derivative of e to the x is e to the x dx. The integral of sine is cosine x. So now, when I multiply the u and the v and subtract the integral of v du, of course, the minus and the negative on the cosine cancel and give me a plus. Here you should notice that you're going to have to use integration by parts again. So I'm going to let u be e to the x again. dv is going to be cosine dx. Differentiate, integrate, and multiply the u and v, subtract the integral of v du. So I get the following. Now, here I'm going to have to integrate by parts again. Or do I? So if you notice up here, you are trying to get this by itself. This is the integral you want, right? So really, we have this big equation. We have that this integral is equal to negative e to the x cosine x plus e to the x sine x minus the integral of e to the x sine x dx. Well, since this is the integral that I want, I'm going to add this integral over to the other side. So now I have two of them equal to the other stuff. And now I can get this by itself, which just by dividing everything by 2. And then, of course, you got your plus c at the end. So you'd actually, if you were to do substitute or integration by parts again here, you'd just be turning over into circles. You would never come to an end. All right, well, I hope you enjoyed integration by parts, and I will see you tomorrow. Have a good night.